Okay, good morning everybody. This is all the solutions to question 8 from exercise 6D in the year 2 book. Basically, it's solving trig equations whilst making use of these new identities that we looked at in the other video on Friday. So, starting with question 1, I'm looking at this equation here, and I've got a sec squared and a tan. I would be thinking about or hoping that the sec squared could be written in terms of tan somehow, because then I'd have a tan and a tan squared. And in ones like this, you really want, that's the sort of thing you're aiming for. My first thought wouldn't be to write this in terms of sec, for example. No, so if we replace sec squared with 1 add tan squared, we can rewrite it equal to 0, and it's a disguised quadratic. We get 2 solutions for tan theta, and we just solve using it in the normal way. Remember, all these trig equations were basically, as they've gotten harder, it's just meant there's been more steps in between to get to a position like this, where it's either sine, cos, or tan equals, and then we can just press inverse and solve. Okay, the next one is done in a similar way. In the brackets here is the identity I've used. Again, it's just about trying things out. You get used to what works and what doesn't. But I'm looking at the sec theta. The squared thing is the tan squared, so I'd be first looking at that and hopefully seeing if that would work if I rearranged it. Bear in mind I've just taken the 1 over, so if sec squared equals 1 add tan squared, then tan squared must equal sec squared minus 1. And we've seen that kind of thing before. Now the tricky part here is that when you try and solve sec theta equals 0, there are no solutions to that, because if you think you're basically saying when is 1 over cos theta equal to 0. Well, if you try to multiply across here, you'd have cos theta, well, you'd have 0 trying to equal 1, which doesn't work. So the rule here is, if you have a fraction equal to 0, there will only be solutions if either the numerator is 0 or the denominator has an infinite range. Okay, so for cos theta, the range of cos theta is -1 to 1. So we aren't going to get any solutions outside of that range. And if you think of the graph of cosec, it looks, this isn't going to be good, but it's like this. So it all makes sense. So if that's sec theta, when does sec theta equal 0, i.e. when does it touch the x-axis? Well, it doesn't, and so there we go, no solutions. But for tan, I'll just jump across to when we have it for tan. When did that happen? Okay. The graph of cot does cross the x-axis. It does have roots. And so whilst we can't say that 1 equals 0, we were basically wondering when is tan theta undefined, and that's at the asymptotes. So you can take it for tan theta's asymptotes, or if you just plot the graph, you should know the graphs, you'll be able to see that cot does have roots, and so it does have solutions for cot equals 0. The rest of this, aside from just those 2 points about when you have sec and cot and cosec equal to 0, cosec and sec are not going to have solutions for 0, so you could just remember it if you want. Cot will, as I just said. So I don't really have much else to say. in the brackets, I've shown what the substitution is that's happening, and then shown how that leads it to be solved. I think this is straightforward, really. You can factorize, or at this point you could just put the coefficients into your calculator. Remember, if you've got cot theta equals 2, we're going to have tan theta equals 1/2, and then we can do it. Now, I've already shown you part D, so you can check that out. Nothing to worry about here. If all of the things inside the trig functions are the same, then you can use the identities in the same way. So it doesn't just have to be, as a basic example, sine squared theta add cos squared theta equals 1. It could be sine squared tan theta add cos squared tan theta equals 1. It could be sine 50 theta over cos 50 theta, and you would get tan 50 theta. As long as they're the same, the identities can be used. And so here I've got the identity that I've used is here. So we have tan squared half theta, that is equal to sec squared half theta minus 1, just as tan squared theta is equal to sec squared theta minus 1. So that might have been a problem. Again, we've got the sec theta equaling minus a half, meaning that we're trying to solve cos theta equals minus 2. Well, you know the range of cos half theta is 1 to minus 1, so we wouldn't get solutions here. F is the hardest one, I would say, for messing around with the identities. On the right hand side, I've written down what each what's going on at each point, basically. So let's have a look. I don't necessarily know what I'm going to be doing here to solve these. As I've said to you before, the trickier they are, the more likely you are to try something and it not work, and then you've got to go and do it again. But I'll get an idea. So my instinct here was to expand these brackets. So I did that, and I get a sec squared theta and a cos squared theta minus 2 sec theta cos theta. Now that looks dodgy, and I would be hoping that sorted itself out somehow, and it didn't remain like that. Because if it was going to stay like that, then none of the identities that we've done have necessarily looked like that. But if I just think carefully about what is going on here, sec is 1 over cos. So we've got 1 over cos times cos, which is just 1. So nicely, that will just become 2. So that's that 2 there. I've also spotted the cos squared theta and the sine squared theta, and I'd be thinking, oh, brilliant, that might make I might be able to use cos squared add sine squared. Now, I can't just make it happen. It needs to be correct, but if I add the sine squared over, like here, then I can replace it with 1. So it's looking nicer, and and the sec squared. So then I'm left with basically sec squared and tan theta, because everything else is just reduced to numbers. And so I can use that sec squared is 1 add tan squared, because then that gives me tan and tan, which is ideal because it can be factorized or just solved as a quadratic. Then I can use the normal way to do that. Now, made a bit of a mess here, so apologies. G hopefully is straightforward now. Steps are there. I've got the tan squared swapping for sec squared minus 1, and then it just simplifies and you sort it out. Remember, the domain is for 2 theta, so I've changed that. I didn't actually write that out, annoyingly. That should be U, shouldn't it? 360. Okay, now the last one I made a mess out of, but this is what I'm talking about. You try something out. In fact, I didn't. It was just I put it into my calculator wrong, so it was okay, but not to worry. Yeah, so it's a pretty difficult one as well, I guess, but the coefficient of tan theta is this, minus, brackets 1 added to root 3. So when you get to that stage, this stage, it's still in a quadratic form because it's got something squared, something in theta, and just a constant. So I put in minus brackets 1 add root 3 into my calculator, and then root 3 there. And I got these two possibilities for solutions, and then I just worked it through. All right, that's a long video. I hope that's okay. Tomorrow we'll be doing more of this, so get a lot of chance to practice tomorrow. All right, cheers, bye.